Hello everyone. Firstly, I would like to thank the organizers of this conference, Cosmology from Home, for giving me this opportunity to present my work. I am Ragavendra from the Indian Institute of Technology, Madras, and I work in inflationary cosmology. I am here to talk about the possibility of producing primordial black holes and secondary gravitational waves from squeezed initial states of primordial perturbations. This is a talk based on a work referenced here below, and this will be the outline of my talk. I will first introduce briefly the conventional method of producing primordial black holes and the secondary gravitational waves. Then I will introduce the mechanism of evolving perturbations from squeezed initial states. We will briefly discuss the methods of calculating the 2-point correlation and the 3-point correlation, namely the power spectra and the bispectra associated with the squeezed initial states. And we will look at the results of the magnitude of primordial black holes and the secondary gravitational waves produced. We will also discuss a serious feature of this mechanism called the backreaction and how that provides a theoretical constraint to this mechanism. I will finally conclude with a brief summary and outlook for this scenario. So, the phenomena of producing primordial black holes or the associated secondary gravitational waves are primarily led by enhancement of the primordial scalar power over small scales. For instance, if there are extremely large value of the primordial scalar power, let's say over the range of small scales like 10 power 9 or 10 power 10 megaparsec inverse, and it reaches of order 10 power minus 2, we can expect those corresponding scales on re-entering the Hubble radius during radiation-dominated epoch can lead to instantaneous collapse of the associated matter density over those scales. These are what are called the primordial black holes, and there are already various direct and indirect constraints on this quantity of FPBHs, which is nothing but the fraction of such primordial black holes that may constitute dark matter in the current universe. Moreover, these enhanced scalar perturbations also source the tensor perturbations at the second order, and they, on re-entry, form what are called the secondary gravitational waves, and they can be quantified by this quantity called omega GW, which is again just the relative energy density between the energy density associated with the gravity waves and the critical energy density of the current universe. Again, there are current and upcoming observational missions to observe and constrain such stochastic gravitational waves in the current sky. But how do we achieve such large enhancement in the primordial scalar power? Well, the conventional method is to introduce features during the late stage excursion of the inflaton field over the potential driving inflation. For instance, if we have an inflection point during the late stages of the inflationary epoch, that can in principle produce the required enhancement in the primordial scalar power. However, one should also note that these features are to be extremely fine-tuned to achieve the required shape and location and amplitude of the spectral enhancement. Is there an alternative, one may ask? There is indeed an appealing alternative, which is the evolution of scalar perturbations from excited initial states rather than the standard Bunch-Davies vacuum. In this method, we do not alter the background, rather excite the scalar perturbations above the Bunch-Davies vacuum and thus produce features in the scalar power spectrum. This method has been already explored in various works over the CMB scales, and in our current work, we will explore this mechanism for producing primordial black holes and secondary gravitational waves over small scales. To briefly review the mathematical part associated, the scalar perturbations that are evolving from such non-vacuum initial states, particularly the squeezed initial states, are given by this expression. Rk is the Fourier component associated with the scalar perturbation, and the quantities of interest to note here are the alpha of k and beta of k, which are essentially acting as the weight for the positive and negative frequency modes in this expression. The alpha and beta here are the good old Bogoliubov coefficients, which come into play when we compute the power spectrum. The 2-point correlation in the Fourier space, which is the power spectrum, is given by this formula, where PS0 is the power spectrum associated with the standard Bunch-Davies vacuum, and the alpha and beta k come into play in this form of mod alpha minus beta the whole square. We essentially seem to have two functional forms to model our desired feature in the power spectrum. However, we should note that the coefficients alpha k and beta k are constrained by this condition of mod alpha square minus mod beta square being 1. So essentially, we have two functional forms to model with one constraint. So essentially, one free functional form to introduce whatever features that we desire using the excited state of the scalar perturbation. We should also note that setting alpha k to 1 and beta k to 0 corresponds to recovering the Bunch-Davies vacuum. So with such a functional freedom, we model the power spectrum using the popular log normal feature of spectral enhancement. Here, G of k is the log normal feature, and it is parameterized in this following fashion. The gamma k determines the strength of the feature over the range of wave numbers. Kf determines the location of the feature, and delta k determines the width of the feature over the range of wave numbers. To obtain the spectrum and to relate the Bogoliubov coefficients to this model of log normal feature, we arrive at the following expressions for alpha and beta of k. Since beta of k setting beta of k to 0 corresponds to Bunch-Davies vacuum, we can note that readily that beta proportional to g and g proportional to gamma denotes the extent of deviation from the Bunch-Davies vacuum. In essence, gamma, the parameter gamma, has quantified the extent a mode is deviating from the Bunch-Davies vacuum. So with this model of primordial scalar power spectrum, we look at the higher order moment, which is the scalar bispectrum, and try to compute the associated scalar non-Gaussianity. It is already well known in the literature that squeezed initial states are known to produce non-trivial and high amplitudes of the scalar non-Gaussianity parameter, which is introduced here as FNL. The scalar perturbation in real space is R, and it can be decomposed into the Gaussian part RG and the non-Gaussian part captured here in the second term. From this definition, we can compute the scalar bispectrum, the 3-point correlation of R, and the power spectrum which has already been computed. And on inverting this relation, we obtain FNL in terms of the bispectrum G and the power spectra already discussed, PS. The bispectra G here requires some lengthy calculation and is governed by the cubic order action governing the scalar perturbations. One can look at the details of the calculations in the references given below, but here we will just state that knowing the scalar modes, exact form of the scalar modes and the power spectrum, we can compute the bispectrum and arrive at the exact expression for this non-Gaussianity parameter FNL in our scenario of squeezed initial states. Having arrived at FNL, we choose to look at the behavior of it in a particular limit called the squeezed limit of the scalar bispectrum. Well, the squeezed limit is nothing but the limit in which one of the three wave vectors constituting the triangular configuration of the scalar bispectrum is taken to extremely small values such that the triangle collapses into a straight line in the space of wave numbers. In such a limit, we arrive at an expression for the FNL in this particular form. Here, we will just take a moment to note the various parameters which are in play. FNL is directly proportional to KF, which is the location of the feature in the range of wave numbers. FNL again is understandably proportional to gamma, which quantifies the extent of deviation of a mode above the Bunch-Davies vacuum. And FNL, interestingly, is inversely proportional to K1, which is the squeezed mode, which is the mode which goes to extremely small values in a squeezed limit of the configuration of wave numbers. With this inverse proportionality, we achieve extremely large values of FNL, which has been plotted here for 4 different values of the sets of parameter values for gamma, KF, and delta K. We choose 4 different values and we take a particular value of K1, say 10 power minus 4 megaparsec inverse, which corresponds to largest scale that is observable today. And we see that FNL deviates from the expected value over the, which is expected from the standard slow roll inflation, and reaches as high value as 10 power 7 over these range of wave numbers. This is the non-trivial behavior of FNL we have been expecting, and such non-trivial behavior will of course lead to non-trivial imprints in the power spectrum itself. So we compute the correction to the power spectrum arising because of this FNL. We again look at the original definition of this FNL and proceed to compute the 2-point correlation of this full scalar perturbation, including the Gaussian and the non-Gaussian part. Understandably, we will arrive at the 2-point correlation being proportional to the Gaussian power spectrum, as well as a part which we can call as PC, the correction to the power spectrum or the corrected spectrum. So this PC is proportional to FNL squared and involves an integral over PS squared. So we already have modeled this PS and we have arrived at the expression of FNL, and we can in principle compute this PC for a given set of parameter values. And with this PC and PS, we can arrive at the full power spectrum and look at how high such power spectrum can be in the scenario of squeezed initial states. So we present such full power spectra in these for the same set of 4 parameter values with the corresponding legends as used before. And we see that even for a small deviation from the Bunch-Davies vacuum, providing such tiny bumps in the original power spectrum given here in red, we arrive at extremely large values from the corrected power spectrum over these range of wave numbers. So this is entirely due to the extremely large value of FNL, and because of such extremely large value of FNL, we arrive at the final power spectrum reaching as high a value in its amplitude as 10 power minus 2. So since we have extreme powers over small scales, we can surely expect the phenomena of primordial black holes and secondary gravitational waves when these modes re-enter the Hubble radius. We compute exactly that, the quantity that quantifies the primordial black holes produced, FPBH, as discussed earlier. For the interest of time, we don't discuss the details of the calculation here, but of course one may refer to these references for the exact details of these calculations. And we compute these the quantity FPBH for the same set of four different parameter values across different range of wave numbers, which here correspond to different mass ranges in the distribution of primordial black holes. We of course have various constraints from direct and indirect observational surveys, and what we observe here is that these intersection of the predictions against the constraint curves not only rule out these parameter ranges, these ranges of FPVs, but they also get related to the enhancement in the scalar power, which we should remember is proportional to the parameter gamma. So the extent of deviation is essentially getting indirectly constrained because of these various observational probes. So this is exciting because we finally have observational probes telling us how high a mode can be excited during its primordial evolution. The same story holds with respect to the calculation of secondary gravity waves also. We have large amplitudes of gravity waves produced because of the sourcing of these enhanced scalar perturbations, and we again have plotted the 4 different sets of parameter values that we have worked with, and we see these constraints overlapping with the predicted curves, essentially constraining the parameter gamma, which again was quantifying the extent of deviation from the Bunch-Davies vacuum. So this seems an exciting result. We also have to take into consideration the theoretical constraint that we mentioned earlier, which is backreaction, and that is quite unique to this scenario of squeezed initial states. So backreaction is nothing but the scenario in which the perturbations may gain large enough energy density such that it can compete or dominate over the background energy density. Such backreaction may disrupt the background evolution, and one has to carefully avoid this ever occurring when we are modeling the relevant Bogoliubov coefficients. The quantity of interest, the energy density associated with the scalar perturbations, is given by this rho r, and it is related to the coefficients in this form of the integral. We know the form of beta of k, so it is straightforward to just plug in and evaluate this integral and arrive at rho r in terms of the model parameters, namely gamma, kf, and delta k. To avoid backreaction, we compare this quantity against the inflationary energy density, which is just 3h squared mpl squared, where h is the Hubble parameter as mentioned earlier. And when comparing these two quantities, one can arrive at the constraint on this all-important parameter called gamma. Now, gamma has to be lesser than this quantity on the right-hand side, where r is the tensor to scalar ratio, but the important factor here is the ratio of k-min to kf, where k-min is the smallest mode possible, or in other words, the largest scale that is observable today, and kf is essentially where we require the feature to occur in the range of wave numbers. For typical values of K min, say 10 power minus 5 megaparsec inverse, and Kf, say 10 power 5 megaparsec inverse, we readily see that gamma has to be extremely small, of order 10 power minus 20 or lesser. Well, one can argue that the tensor to scalar ratio has to be also accounted for, and we can reduce some of the constraint on parameter gamma by making R go extremely small. But however small we can go, even as small as 10 power minus 30, gamma cannot be significant enough to affect whatever arguments and calculations that we have performed earlier. In other words, this strict constraint on gamma essentially kills the extremely large value of FNL that was produced, and hence kills these large amplitudes of power spectrum that we arrived at, and hence wipes out any significant amplitude of FPBH or omega GW that may be produced from squeezed initial states. So this seems a result that is counter to our expectations, in that the issue of back reaction strictly renders the scenario of squeezed initial states unfeasible for production of primordial black holes or secondary gravitational waves. So in summary, we saw that the mechanism of evolving perturbations using squeezed initial states is rather a promising mechanism to produce primordial black holes and secondary gravitational waves. It indeed produced large magnitude of non-Gaussianity parameter, and hence a corresponding large amplitude of correction to the power spectrum. However, the issue of back reaction strongly constrained any deviation of the initial state above the Bunch-Davies vacuum, thereby severely limiting the production of primordial black holes and the secondary gravitational waves. However, there is a positive note to end with, as in the non-Gaussian corrections that we have calculated is sufficient insofar the omega GW is concerned. However, the FNL can also directly modify the probability distribution of the matter density that can collapse into PBHs. So the non-Gaussian effects due to squeezed initial states affecting FPBHs directly have to be analyzed separately. Moreover, it is also interesting to calculate higher order moments such as the 4-point correlation or the tri-spectrum to see if we can get stronger enhancement to the scalar power within the limits of back reaction. With this, I thank the audience for your attention, and I will leave with the slide containing the reference for my talk. Thank you.